My name is Tevin Howder, and this is my audience. 251.9 million years ago, some 90% of all life was wiped off the face of the planet by a mass extinction that would change the course of life on Earth forever. This catastrophic event is known as the End Permian Mass Extinction, or PTME, and marks the boundary between the Permian and Triassic periods. By the end of this apocalyptic extermination around 8 to 20,000 years later, nearly all life had been driven to extinction, giving it the title The Great Dying. But how did this happen? How could so much death occur in such a short amount of time? What could have triggered a mass extinction that so severe it nearly destroyed all life on Earth? Today, I'm going to inform you about the causes of the End Permian mass extinction. Even though the Great Dying occurred hundreds of millions of years ago, it still holds relevance today. In an article published in the journal Paleogeography, Paleoclimatology, Paleoecology on July 15, 2017, titled On the Causes of Mass Extinctions, paleoenvironmental scientist David P.G. Bond wrote, "The realization that Earth is once again facing some of the stresses implicated in its past crises has intensified debate over the causes of mass extinctions, and yet we have very limited understanding of how either terrestrially generated or extraterrestrial stresses actually affect ecosystems. By studying the Permian extinction and events like it, we can grasp a better understanding of our planet and the struggles it faces today. I have always been interested in paleontology and natural history, and I am passionate about conservation. I've done extensive research on this topic, so I'm excited to share this information with you. In this speech, I will first discuss the gradual hypothesized causes of the Great Dying, followed by the catastrophic causes. The causes of the Permian extinction are often grouped into two separate groups, gradual and catastrophic. Gradual causes include acidification and climate change. Ocean acidification is defined as the gradual increase of acidity in the ocean, usually due to the absorption of carbon dioxide from the atmosphere. This process results in anoxia, the lack of oxygen in an environment. Bond reports that anoxia was the first extinction theory to be widely accepted as a cause for marine extinctions in the Permian. By looking at the chemical and physical properties of rock layers dating to the Permian, scientists have discovered ample evidence for oxygen depletion. Ocean acidification also causes hypoxia. Professor of vertebrate paleontology Michael J. Benton published in an article, Hyperthermal-Driven Mass Extinctions, Killing Models During the Permian-Triassic Mass Extinction, in 2018 in the journal Philosophical Transactions of the Royal Society A. Benton defines hypoxia as deficiency in the amount of oxygen reaching the tissues. He states that larval organisms and smaller organisms are intolerant to hypoxia. Another gradual method is natural climate change. Benton reports that oxygen isotopes suggest a rise of 8 to 10 degrees Celsius in the Permian-Triassic boundary. This equates to a devastating 46 to 50 degrees Fahrenheit. By comparison, the measly 2 degrees induced by the Industrial Revolution seems minuscule. The rise in seawater temperatures is even more dramatic, suggests a study by postdoctoral researcher Jana Gliwa published in 2022 in the journal Paleontology, titled Gradual Warming Prior to the End Permian Mass Extinction. By analyzing oxygen isotope ratios in the fossilized shells of tiny crustaceans, it was found that seawater temperatures rose by approximately 12 degrees Celsius, or almost 54 degrees Fahrenheit, at the beginning of the main extinction event. At the height of the PTME, water temperatures reached between 100 and 108 degrees Fahrenheit. Gliwa's results also suggest that temperatures in the Permian had been rising for at least 300,000 years before the PTME. Evidence also indicates mass migrations. As reported by Benton, in a study based on the skeletal and footprint data, details of these migrations were detected. With a clear geographical disjunction through the PTME, with tetrapod distribution shifting 10 to 15 degrees poleward. Many scientists suggest that the extinction was also induced by several catastrophic causes. The event of an asteroid impact or bolide impact causing the End Permian mass extinction is a familiar idea. However, finding a possible impact site is near impossible. Karen Wright published an article titled The Day Everything Died in the journal Discover, in which she explains the Earth's crust is never static. The ocean floor recycles itself every 200 million years, wiping clean any evidence of an impact on the ocean floor. It would be like stabbing a man with an icicle, a murder with a weapon that vanishes. Another possible catastrophic cause for the extinction event is the release of methane. Methane poses a huge risk to the ozone layer. which protects the Earth's atmosphere from harmful solar radiation. A large-scale release of methane would have depleted the ozone layer, exposing the planet to radiation. One likely source of methane is through the release of methane hydrate, also known as methane clathrate. Bond states, during cold periods of Earth's history, as in the present day, extensive deposits of gas hydrates can form by vertically migrating methane. Deposits of gas hydrates can form by vertically migrating methane being trapped or frozen in the hydrate stability zone. This can occur within sediments in both marine and terrestrial environments that are in the correct pressure and temperature stability range. Global warming can lead to melting of hydrates, releasing methane that further amplifies global warming, in turn destabilizing more hydrates, which furthers warming effects. This forms a positive feedback loop referred to as a clathrate gun, and has been suggested as a mechanism for runaway greenhouse over geologically very short times. The final, most likely, and most dramatic hypothesis is increased volcanism. A large-scale volcanic event being behind the largest mass extinction in the Earth's history is one of the most catastrophic and climactic possibilities imaginable, and such an eruption could trigger many of the causes listed prior. The most likely perpetrator of a volcanic eruption large enough to cause the PTME is the Siberian Traps. The dates of rock from this basin correlate nicely with the timing of the Permian extinction. Located in Siberia, this is one of the largest volcanic rock basins in the world. In 2019, postdoctor at L.E. Oglen published an article in the journal Scientific Report, titled "The Main Pulse of the Siberian Traps Expanded in Size and Composition." In this article, he and his team produced data that supports the estimate size of the Siberian Traps at 5 million square kilometers. This equates to almost 2 million square miles, almost twice the size of Argentina. To further the extent of this eruption, geoscientist Linda Elkin-Stanton led a study titled "Field Evidence for Coal Combustion Links the 252 MA Siberian Traps with Global Carbon Disruption," published in the journal Geology in 2020, which discovered direct evidence that the eruption of the Siberian Traps combusted coal and rich organic material, contributing to carbon dioxide emissions and furthering global warming. When volcanoes erupt, they eject tons of matter in the form of gas. Bond states that the two most important volcanic gases are carbon dioxide and sulfur dioxide, greenhouse gases. Sulfur dioxide, or SO2, causes warming over days to weeks, before transitioning to cooling effects. SO2 produces aerosols that block sunlight and last 2 to 3 weeks after an eruption. Carbon dioxide, or CO2, causes significant warming over long periods. Warming reduces the capability of water to dissolve oxygen, causing the acidification discussed earlier. Acid rain is another side effect of increased volcanic activity. Bond writes, acid rain derives from the reaction of SO2 with moisture in the atmosphere to form sulfuric acid, and in recent years it has been suggested that sulfate aerosols derived from the Siberian Traps may have produced strongly acidic rain in the sufficient volumes to adversely affect Permian terrestrial ecosystems. The acid rain produced by the eruptions was devastating. Benton reports that the pH levels of acid rain could have reached 2 or 3. This is comparable to the pH of vinegar or lemon juice. Global biodiversity took a long time to recover after the PTME, and the possible causes of this annihilation could explain how it all happened. Gradual causes, such as acidification and climate change, gradually chipped away at life, applying more and more pressure on the planet. Catastrophic causes, such as an asteroid impact, methane release, or volcanism, quickly destroyed ecosystems, pushing the planet over the edge. As we learn more about Earth's past, we can apply our knowledge to Earth's present to help preserve it for future generations. Even though the largest extinction event in Earth's history is long gone, its relevance is still striking and intimidating. As we learn more about our past, we can take control of our future. Thank you for listening.